Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use Coulomb's law to calculate the net force on a particle due to a system of charges. So what we're looking at here is we've got three charges. We've got a charge at the origin here at the point that I labeled 0, 0, and I'm going to call the charge on this plus Q. Then we've got another identical charge here over and down at the point A minus B, and again same charge plus Q. Then we've got a third charge here that's going to be negative in this example, but same magnitude of charge at the point AB. And what we're going to do here is talk about calculating the net force on the charge at the origin. Now, first of all, you may ask, well, why the one at the origin? And the answer is I just picked one out of a hat. I could, for the sake of an example, find the net force on any one of these three charges. The one at the origin does end up being, I think, the quickest and easiest, and I want to keep this video kind of short. So we're going to take a look at finding the net force on this charge. Now, anytime you're asked to deal with force vectors, you should always draw those force vectors. So I'm going to go ahead and draw a force vector on this charge. The force vector on this charge due to this guy is going to be an attractive force, so that force is going to point up and right. Now if I were to give these charges names like maybe 1, 2, and 3, then I might call this something like force 1, 2, force on 1 due to 2, or force on 1 from 2. Now, I'm going to go ahead now and calculate the magnitude of this force right now. So by Coulomb's law, I'm going to write this off to the side. Remember, the force between 2 point charges is K, Q1, Q2 over distance squared. In this example, the Q1 and the Q2 are the same, so I'm just going to call that KQ squared over. Now, the distance we need is from here to here. And if you take a look at this triangle right here now that I've drawn, this horizontal distance is A, this vertical distance is B. So this distance squared is equal to A squared plus B squared by Pythagorean theorem. So I'm going to go ahead and just put A squared plus B squared in the bottom. So there's the magnitude of force 1, 2. Here's some sort of angle theta, which I'll talk about later, or we'll deal with it when we need it. All right, next, these two forces are going to repel one another. So when I draw the force vector on this charge, that force vector goes like, I guess right through my coordinate there, but up and left. And if I call this force 3, a logical thing to call this force would be maybe F13. Now, Q1, 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 all of these charges are the same in this example. I did that just to make this kind of a nice smooth example, which means, again, I can write this as KQ squared. And by the way, the distance here to here is the same as it is for here to here. If we look at this triangle right here, again, that distance is A, that distance is B. That makes this distance the square root of A squared plus B squared, but in the bottom here, we're going to be squaring that distance anyway. So A squared plus B squared. Also notice, I'd like to go back, you'll notice that I didn't even bother including the sign here, even though this charge was negative. Again, it's important to realize, what do we use the minus sign for? I used it when I drew this force vector up and to the right. I used it when in the fact that this was an attractive force. At that point, you don't need the plus and minus signs anymore. These are force vectors we're dealing with. They'll be plus or minus based on direction, right, left, up, down. Now there's some sort of angle theta here. If you look at the symmetry of the problem, these two angles are the same. So let's see, now let's start talking about adding them. Notice that the magnitudes are the same and these angles are the same. So when we add these force vectors, their x components are going to add to 0. So I'm just going to state that over to the right. Fx is going to be 0, and I'll just say by symmetry of the problem. Most people, if you're taking a physics class or something, most instructors I know would accept that as work for the horizontal components of this. Some may not, but I think most would. All right, next we'll talk about the y components. the y component of the net force vector is going to equal this guy's y component, which is going to equal kq squared over a squared plus b squared times the sine of the angle theta. Now, I'll deal with the sine theta in a minute. I'm just going to talk about this guy right here. This guy has exactly the same magnitude times the sine of exactly the same angle. So when we add these, I'm just going to multiply this by 2 for the fact that there's 2 of them, one here, one here. We're going to basically call that done. In my next line, let's see, we're going to have 2kq squared over a squared plus b squared. Okay, now we'll deal with the sine theta. This time I'll leave the triangle there. All right, so I'm going to get that from this triangle. This side right here is b. This side is going to equal the square root of a squared plus b squared. So sine theta is equal to b over square root a squared plus b squared. I'm just going to go ahead and multiply that, b over square root a squared plus b squared. And basically there's my net force. That net force is vertical. And let me write that out in vector language now. So the net force acting on charge 1 is going to equal this expression, 2kq squared times b over. These can kind of be absorbed together. If you take a squared plus b squared to the first power times a squared plus b squared to the 1/2 power, you get a squared plus b squared to the 3/2 power. And to give this or make this a vector, I'm going to give it a direction plus j direction in terms of the coordinates shown. I can write a better j than that, I think. Good enough. So we got right positive, up positive, plus j direction would point up. So there's an expression for the net force vector acting on charge 1. And again, I could have also decided to find the net force on charge 3 or 2. I just picked one for the sake of example. I hope that this helps demonstrate how to deal with Coulomb's law and find force vectors. Have a great day.